Well, hello and welcome back to the Watt Hour. This is episode 11, and I'm William Hadala. And today we're going to climb to the edge of space without ever leaving our seats. And my guest is Russ Van Der Werff, who is the president from the HAPS Alliance, a global coalition dedicated to advancing high altitude platform systems. Now, these aircrafts operate in the stratosphere, and that's like 65,000 feet up in the air. And they're delivering connectivity and surveillance and data from above the weather, below the satellites in space, and far beyond the reach of conventional aircraft. And today, our goal is to dig into what a HAPS aircraft really is, where it's used, why it matters, and the engineering that keeps it in the air for days, weeks, or even months at a time. We'll also get into battery integration and power demands and what it actually takes to make these platforms viable long term. So, Russ, welcome to the Watt Hour.
Thanks. It's great to be here, William.
That's awesome. So let's get start right at the top, literally. From your perspective, what exactly is a HAPS aircraft, and how does it differ from traditional UAVs or even a low Earth orbit satellite?
Yeah, I think you touched on it some in your introduction, but at a high level, pun sort of intended, what we're talking about are a variety of flight vehicles that are operating, say, between 50 and 100,000 feet. Some of them are solar powered or hydrogen powered aircraft. Some of them are balloons or propelled airship designs. And like the thing that's unique about the stratosphere is you have some of the advantages of space where you're above all the turbulence and weather and things are associated with where a normal aircraft would fly. But you're still close enough to Earth that when you're doing connectivity or Earth observation missions like that, it's more like an aircraft in that you can get really good quality connectivity or sensor data. When you're flying satellites, you kind of have the two options, right? The low orbit satellites that are whipping over, and you might get a couple passes over a certain point on Earth every day for a few minutes. And so if you want to make that effective for continuous operations, you got to have a lot of satellites. Or you've got your geostationary satellites a long ways from Earth. It's in one place over the ground, but you're very, very far away. And so it's hard to do things like connect data to cell phones or take pictures without a very big and expensive camera. So what HAPS offers is something in between, right? It's much cheaper and more operationally responsive. We can get it in the air quickly. It's more like an aircraft in that sense, but it's got a lot of the attributes that make a satellite useful for remote sensing or communication because it can loiter over a certain area, persist for a long period of time, and not be subject to things like weather and turbulence and things like that.
I've often wondered, Russ, it's a long ways up to 65,000 feet, and you do have to go through some weather to get up there. How do these things actually get up to altitude?
Yeah, you talked a little bit about engineering, and there is a real engineering challenge in there. Now, we talked about some of the different kinds of vehicles, so it's very dependent on what we're talking about. Something that's a lighter than air, HAPS, like a balloon or an airship, is basically filled with lift gas and released and then ascends to orbit. Something that is heavier than air, like a solar or hydrogen powered propelled aircraft, has to navigate up to that altitude. And because operating at that altitude is a unique environment. The temperatures are very low, the air density is very low, so designing an aircraft is very different. Think very lightweight, very large wingspan, things like that. The actual pattern of climbing up to altitude and climbing back down through those turbulence layers is a major part of the engineering design process to make sure that the system can survive that. However, it is a very short period, relatively speaking. Most of these platforms are designed to fly for weeks to months, as you mentioned, even over hundreds of days at a time. And so you're talking about, minutes to a couple hours on either end of that flight pattern where you're in airspace that other aircraft are operating in, which means, it's fairly straightforward to coordinate with air traffic control and stuff. You're mostly up above where nobody's bothered for most of the flight profile.
It's fantastic. Now, when I look at the images, I see things incredibly long with thin wings and lightweight frames and high aspect ratios. And I know that's deliberate. Can you walk us through the design priorities, like from an aerodynamics perspective and weight management and material? How do you handle thermal cycling in such extreme conditions?
Yeah, for sure. So again, I guess just breaking it down into the kind of two kind of classes of vehicles, we have heavier than air and lighter than air. So for the aircraft, the traditional, what you'd think of as an aircraft, heavier than air vehicle, you kind of alluded to it and you kind of hit it on the head, but there's a really complicated set of trades that has to be worked. You need something, first off, large, high aspect ratio. What that means is, long, skinny wings that go a long ways out. The reason you need that is because getting lift at that altitude is really challenging when you're moving very slowly and there isn't very much air up there to traverse the wing and provide that lift, right? We're talking about a few percent of the air density that you'd have on the ground, very space-like conditions. And I would say, one of the reasons that these platforms are emerging now and really haven't in the history of our 100 or so years of powered flight that we've had with fixed wing aircraft is the technologies that are enabling that. So, in order to have something that is durable but very light and very long, the material science that goes into designing these aircraft is really complicated. And we're talking about exotic structural designs that are using, fairly new techniques to build. And then also, the thing is, once it's up there, keeping it up there means you've got to stay powered. You got to propel the thing at a speed that's sufficient to move air across the wing and keep the lift. And so that power equation, as you also mentioned earlier, is really important too. So you need to be able to provide enough energy to keep moving at enough speed to stay airborne. And another technology development area that has really enabled this product to exist is things like solar and battery technology and the energy density or the energy to weight ratio, if you want to think about it that way. And as you know, those technologies are being pulled along by lots of industries right now, both the battery storage, energy storage, and the solar technology. But really, over the last, say, 20 years, we've gotten to the point where, good enough ratios there to keep a heavier than air vehicle continuously in flight for the first time. So that's for the heavier than air side. Now, on the lighter than air side, you have different challenges. So lighter than air vehicle would be filled with a lift gas like helium or hydrogen. And there you have a structural challenge too, which is, as you mentioned, there's a strong thermal variation day to night. So you're taking in a lot of sun in the daytime, and then it's very, very cold. We're talking minus 80, minus 90 centigrade at night. And so designing an envelope that contains the gas as it shrinks and expands and puts pressure on that envelope through those conditions for, again, hundreds of days repeatedly at a time is also structurally very challenging. And then, of course, the same questions about keeping enough energy to operate and having light enough, effective enough solar and everything. I think those are the technologies that have really brought us to where this is operational recently.
That's fantastic. That and amazing. Now, I'm most interested in power. Now, up there at 60 to 70,000 feet, you've got an abundance of sunlight during the day. When you said it gets extremely cold and it's long nights sometimes. How are the battery cells and packs actually integrated into the airframe? Are they like inside the wings? Are they in the fuselage? And what chemistries do you find are the best to handle those nighttime temperature extremes?
Yeah, so I mean, first off, on the integration side, a lot of it really depends on the shape and nature and size of the aircraft that we're talking about. So, when you're talking about the solar powered, electrically charged aircraft, for the most part, their challenge is distributing mass through that airframe. And again, that airframe, it works because it's very large and very light. So there's a twofold problem there, right? Distributing mass because you don't have a lot of mass to play with, but also structurally, you can only afford to put that load at different points in the airframe. And so the real trick on those is what is the best energy density, again, that I can get. So the lightest battery with the most energy storage. And then typically, as you mentioned, it's distributed throughout the aircraft, say in the wings or other parts to get enough concentration up there in total to do the powering. Now there are a lot of different designs. There are also systems that are powered by like hydrogen fuel cells. That tends to be a more energy dense storage medium, and so it can support a more traditional aircraft design where you concentrate those fuel cells in the fuselage. However, it's not renewable the way solar is, and so the duration of your flight won't be as long as a solar vehicle, which can fly semi indefinitely. Obviously, everything wears out eventually. Um, and then, of course, again, back to the inflatable or lighter than air systems. For the most part, they're not aerodynamically constrained, right? And so, but you still have that benefit of how much power can I get for how little weight? And so we're always looking for new chemistries. I'd say the cell packaging is a unique challenge, and there's a few different things there. One of the things is we talked about the atmospheric pressure and the thermal cycles. So cells that are expand and contract naturally under those conditions are a challenge mechanically to figure out how to package safely and securely so that allows for that fluctuation. And then there's also temperature management. If you know anything about, as I'm sure you do, thermal management on battery cells, there's an optimal working temperature, especially if you're pulling a load on them. And then there's this trade, right? Like you can apply thermal control to keep those cells in the right temperature range, but you're spending power to heat the cells, and so is the power you're gaining by being in that sweet spot. So there's a unique kind of pack design, I'd say, that most vehicles are doing a unique pack design to suit what their vehicle can support. And then, you talked about chemistries. I mean, most of these vehicles that are running on battery and solar aren't using real exotic chemistries, but I will say that within your standard lithium chemistries, there are companies that specialize again in getting that maximum energy density, and how they construct the cell has a lot to do with that. And I am not a battery cell designer, but I have sat through presentations where they use a lot of chemistry-like words and tell me about how great the process is. But at the end of the day, as a vehicle designer, which is kind of where I work, it is a bottom line, how much power can I pack and how little weight? And we're really seeing some very efficient, very impressive numbers over the last 5 to 10 years as people are optimizing for this market.
No, optimization's the right word for it, especially phase change material, especially when you're at such extreme cold temperatures
Yeah,
and as well as
it's a
hot.
very
And
unique environment. It's a challenge from an engineering perspective for sure.
yeah, so when you're up there at 65,000 feet, I've often wondered, what's the weather up there? I hear that it's actually fairly calm. Is that correct?
Yeah. So the stratosphere is the layer above what we call the troposphere. The troposphere is the atmosphere we live in, right? And it's where all the weather happens. The stratosphere, there's a temperature incline right between the thermosphere and the stratosphere, and it depends on where you're at in the world and what time of year, but say 30 to 50,000 feet above that. The reason it's called the stratosphere is it tends to be stratified. So strata is a Latin word that means layers, right? And so it runs in different circulating layers of wind that are fairly benign. So we're talking about typically, no moisture, very little vertical convective turbulence, not none, but relatively little, especially relative to the troposphere, and then different wind vectors running at different angles throughout that span of altitudes. And so, most of the platforms up there are taking advantage not just of how relatively benign the conditions are, but also of doing predictive modeling on what direction the winds will be going at what altitudes, and using that to assist in flight path planning and energy management. And obviously, you want to be going with the wind, to minimize your expended energy. So, yeah, it's pretty calm. It's stratified. It's in setting in layers, and it's kind of above all the moisture and weather in those kind of considerations.
And so for a fixed wing aircraft at that altitude, how fast does it need to be going in order to maintain that altitude?
Yeah, I mean it varies a lot based on the design, but we're not talking real fast. We're typically talking tens of knots. So it's not a game about getting there quickly, but of course, when you're trying to persist over an area for weeks or months at a time, going slowly is actually an advantage, right? You can keep sensor on target, you can keep that communications link going because you aren't zipping by at 200 knots, right?
Exactly. So let's talk about use cases and strategic relevance. And so let's connect the tech to the mission. Where are
Yes, sir.
HAPS aircraft actually deployed right now? And I've seen everything from extending LTE coverage to wildfire monitoring. What's in service today? Just give me an understanding of that.
Yeah, I mean, you mentioned a couple of the big ones that have been demonstrated, LTE coverage, especially in an augmentary, like there are places that aren't well served by the existing network. And you can deploy a high altitude platform, cheaper and quicker than building out physical infrastructure, especially in challenging environmental conditions or places with limited infrastructure to start with. The other case we're looking at a lot with LTE or cellular coverage is disaster response. So, um, when Hurricane Maria hit Puerto Rico 7 years ago, Google Loon had a constellation of high altitude balloons over the island for about 2 months, providing cellular coverage until they could reconstruct the local infrastructure. So that'd be another example. Wildfires, there's really three parts to the wildfire use case. One is early detection. So having a persistent stare, so that we can keep eyes on for new starts. A huge part of wildfire management and containing wildfires is knowing quickly before something spreads out of hand how to get to it. Um, and there are some dedicated satellites for those things, but it's hard to build a constellation of dedicated satellites for every specific thing you want to do. Where high altitude platforms excel is persistent applications that are regional and seasonal. So we can put the thing up there, keep it there for a few months over a specific area, and then bring it back down. It's very cost effective. So wildfire detection, but also real time monitoring during the fire. So we've been seeing things like using infrared imagery to distill a perimeter of the fire and then using that cellular connection down to somebody's phone to real time give that firefighter situational awareness of where the movement of that fire is, which hard to believe maybe, but today that tends to be a cadence of maybe a couple times a day they get some kind of an update that somebody's hand producing. So that's a huge benefit there. Another one that's maybe interesting is methane leak detection. We've seen a couple of companies doing that. So looking at monitoring oil and gas infrastructure to find leaks quickly before they create environmental damage. This is another area where you have a very wide area that you're trying to monitor because this equipment is spread over a very large area, and you need dedicated sensing equipment of a certain type to find that kind of an anomaly. So those are all interesting commercial applications. And then there's quite a bit of interest on the defense and government side too. And it's really crossover if you think of it as Earth observation and communications as two verticals this way, and then you go this way is to say, well, there's a civil or commercial side and there's a defense side for both of those missions. And we're seeing a lot of interest and traction both in the observation and the communication applications for defense as well.
So somebody comes up with a use case and they say, "Man, that's a perfect mission up in the stratosphere." It's a make versus buy decision. Do they have to make their aircraft, or are there companies out there that will actually lease their aircraft for these types of use cases?
Yeah, there's a wide variety of business models in service, anywhere from sales of aircraft to pay by the flight hour service, available in both fixed wing and lighter than air. So if you look at our website, you can go see the member companies. I work at Aerostar, which is just one of them. I got the shirt, so I guess that's obvious. But there's a good dozen companies who are building different shapes, sizes, and constructions of high altitude vehicles, lighter and heavier than air vehicles that are out there today and doing these operations. And you know, a lot of that depends on the application and the customer and kind of how they're used to operating. So there are some advantages. When you put something up in the air for months at a time, you can actually serve multiple customers and multiple missions in succession and get real cost efficiencies. So there's a lot of people looking at kind of the flight pay by the hour or data as a service type models. But there are also applications like some of the more sensitive security applications where they want to have their own system that they operate and the vendor has no hands on with it. And so I think you'll see all of those business models out there.
Yeah, and that's what episode 10 was all about, was military capabilities as a service. And so when we look at, HAPS is often pitched as an alternative to satellite. So let's just call it out. Where does it beat satellites hands down, and where can't it compete?
The way I always like to approach that conversation is you need different tools for different jobs. So HAPS aren't going to put satellites out of business or traditional aircraft, but I'd say just circling back again to that, you need a responsive system, something you can put in the air on demand, or at least with, weeks or hours of notice instead of months or years, like with the satellite traditionally. You need something that is regionally persistent. So again, satellites are pretty good at zipping around the Earth, but you need a whole constellation of them to be persistent in that use case. HAPS, you can go take it and park it over an area for an extended period of time. And then, that again, just being closer to the ground. I think, one of the analogies that another one of our members did at a presentation I was at, so I give the credit, gentleman from Nokia, was talking about communications, and he's holding up an apple, and he says, look, the skin of this apple, like the outside of the skin of this apple is where your HAPS is at relative to the Earth. And then the other end of the room is where your geostationary satellite is at. And so there's just physics in the way, right? Like if you want to do communications, you have a lot of latency, a lot of time for the signal to travel out to that satellite and back. If you're trying to take pictures, and you want good detailed pictures of something, I mean, that's a long ways away to take a picture. So it's basic physics stuff where just physically being in that stratospheric layer instead of out in space gives you a lot of advantage there too. Um, I think cost is the other thing. I mean, these systems to build, implement, and operate are much, much cheaper than a satellite or a constellation of satellites. So, if you look at something like what Starlink has done, which is just incredible, is democratize satellite communication through a satellite terminal. But that is a market where everybody needs that thing, right? Compare that to methane detection. We can't afford to send 4,000 satellites up in a constellation to do that. It's too specialized. And so the cost to implement a system like that with the HAPS is much lower. So that's another area where you can win out. But again, it's not the be all end all. If you want full coverage of the whole Earth all the time with an effect or something, satellites are a better solution for that, right? If you want to put something up there and just have it there for 10 years running, doing the same thing, and you aren't going to need to service, refresh, update the payload, the effect, satellites are a good thing there too, right? So it's not like it's replacing, but it's filling in some gaps that are hard to do with the current technologies.
So, to some of our viewers that had worked with me in years prior, I used to build towers, cell phone towers, from 90 feet to 400 feet. And
Yeah.
those towers would range in cost from, a couple 100,000 upwards to 500, $750,000. So when I think about parking at altitude, one of these platforms, maybe somewhere in Africa or a remote region of the world, to provide connectivity to the ground as well as maybe beaming and relaying power one day, the cost of these aircraft, right, would be probably the equivalent of building a tower, but with the mobility versus the millions and tens of millions associated with the satellite in space.
Yeah, I mean, rough orders of magnitude, in the HAPS world, we're talking about hundreds to thousands to maybe tens of $1,000s an hour to operate across the spectrum of platforms. Traditional aircraft, even a small unmanned aircraft that the military would have in service, when you factor in acquisition, maintenance, and crewing, we're talking about tens of thousands to hundreds of thousands of dollars to operate. And so it is an order of magnitude or two difference in the cost perspective versus aircraft. And that is where you really can start to see it as a viable alternative to some other more ground-based or traditional infrastructure deployments, as you mentioned.
That's fantastic. So, of course, none of this happens without regulatory clearance. And what's the latest on airspace integration and spectrum allocation for HAPS? And are we moving towards a global standard?
Yeah, you touched on a topic that's very close to my heart and a very big deal for the HAPS Alliance. I don't know how many people out there get excited when you say airspace integration and telecommunication regulation, but I do, because we need it to make this work. And so within HAPS Alliance, we have three functional working groups that are working different policy areas. One of them is aviation regulation. One of them is telecommunication regulation. One of them is defense applications. And those are all things that have their own unique policy challenges. Um, we're working real hard on a lot of fronts on the aviation regulation side. So some of the bodies, and just to throw the alphabet soup around, obviously within the US, the FAA and NASA are responsible for all that. There are several working groups looking at how we're going to do air traffic control in what they call E above A, which is buzzword soup for, really high altitude that isn't regulated today. So, there's a group, an FAA NASA joint group that's built like a conceptual deconfliction tool, and several vendors are feeding data into it as they do flights. So we're working towards that. If you go more globally, ICAO is the organization that is the global airspace organization. What they do is provide guidance and standards for all these countries to adopt on how to do airspace management. And we've got a working group that we're also represented. Our consortium of HAPS Alliance is represented with working with them on trying to help define those early stage views. Now, if you think U.S. regulatory moves slowly, international regulatory takes a lot of time, get a lot of stakeholders, and so we're talking about getting interim guidance out in the next few years, and then we have a 2030 target and a 2040 target. But at the same time, these companies and these capabilities are just coming to maturity, and so there probably aren't thousands of these things in the air right now at any given moment in time. So we don't need that super intensive regulatory oversight yet. And we're trying to build towards how will that look, trying to basically get ahead of what happened with small drones in lower atmosphere where the systems were ready and the regulatory wasn't, right? We want to be ahead of that curve. Um, I think that'll yield good results. I mean, we're heavily engaged, in having a group like ours that has all the different vendors pushing together allows for all the perspectives to be represented. So it's probably the thing that for my personal company, my day job, I'm most excited about that the HAPS Alliance is doing. Um, then we could also talk about telecommunication. You got to control these things, so they need to communicate to the ground or up to satellites. And then if they're providing coverage and things like that, that requires regulatory guidance too. That's really interesting because it crosses borders. And so when you're beaming down power or communications through free space across, from 70,000 feet, you can see several hundred miles in every direction. So you might
Right.
be seeing multiple countries from where this system is. And so there's a really important piece of getting unified requirements there, and that's working with groups like the ITU, which is the International Telecommunications Union, and getting pre-gaming those things. Also, a lot of support from what's called 3GPP, which are the groups that regulate how cell phones work, and how the communication handoff between these platforms. Uh, NTN is a buzzword in that space right now, and it's like node-to-node communication. You might be talking from your phone to a HAPS, and then roam over to a satellite, and then you drive a little further, and now you're in range of a tower again, and that whole system is being developed quite actively by the cellular folks working towards that. So a lot that we're doing there in both those fronts.
So when you look 5 years down the road, what are the biggest technology leaps you expect to see? And are we talking next gen, um, you know, chemistries for batteries or lighter airframes? And where do you see this whole movement going into the future?
Yeah, I mean, all of those things move the needle. And like I mentioned earlier, the thing that really excites me is all of those technology pieces are being pulled along by multiple industries. So we don't really need extreme focus on HAPS development. I think the battery and the solar and the structural things, there are optimizations, but those things are all tremendously further along than they were 20 years ago. And in 20 years, I think they'll be tremendously further along again. And so the natural consequence of that, I think, is that you're going to see more and more vehicles operating at this atmosphere. We're starting to see operational use now in some of those areas we talked about. And that's just going to grow as the things get more efficient, more cost effective, longer duration, et cetera. So I think you're going to see a lot of excitement in this space, tech development, a lot of aircraft in the air. And then the other piece is, when I look just even 5 years out, like I mentioned, hoping to get the regulatory piece sorted a little better. Different vehicles in this space have very different regulatory environments right now and different certification and safety environments. And that's because most of these rules were not written with HAPS in mind. So they're taking other rules that were meant for other systems and trying to apply them to what we're doing. And we really got to get that unified, straightened out, and aligned such that, we can get. I mean, engineers can engineer all day long, but if you don't know what the requirements are, it's real hard to meet them, right? So we got to get those constraints on what we can and can't do and how we're going to do it defined to get that operations to scale as well. And again, that's something we're pushing real hard on as a trade group.
So you mentioned a day job. So Russ, tell us a little bit about you and your career, what you do, and how you got involved with all of this.
Yeah, sure. I mean, so I'm an engineer by background. I work at Aerostar. One of the things that we do is lighter than air HAPS, so balloon-based navigationally enabled stratospheric vehicles. You know how I got into it? Well, I was a very young boy and I was studying the stratosphere. Now, I look, I worked in telecommunications at a satellite communications company for over a decade. I was interested in a change. I started looking around and I came across Aerostar, and it's kind of like, you do what with balloons? That's a thing that anybody does, and that kind of attracted me. It's like, yeah, I want to do the thing that nobody else does and figure it out. And I think it's still motivating for all of us in this industry that every day we're coming to work and we're doing things that nobody's literally ever done before. I mean, there's just not that many places in the science and tech world where you can say that right now, and it's really cool. So, still gets me up in the morning every day for sure.
And if you had unlimited budget with, what single breakthrough would you push to make perhaps beyond regulatory to truly make this ubiquitous?
Yeah, I mean, look, if you look at the HAPS problem really broadly and you exclude regulatory and you just think about tech breakthroughs, I think energy is the game, right? I mean, you said it earlier, and it's sorry, thought I'd muted that. Say, if you look at just tech breakthroughs, I think energy is kind of the game. I mean, you said it earlier, and the reality is that these systems can't operate without power, and the more efficiently we can power them and keep them running, that's crucial. Um, I think if you want to get a little more esoteric and think about something nobody's thinking about, wind modeling is really important to most of these vehicles. I mentioned it earlier, but it really does drive what we can and can't do. And numerical weather forecasting's been around for about 100 years as well. Most of that time, people care about, whether it's going to rain tomorrow. They don't really care what direction and speed the wind's going at 72,800 feet. That's just not a problem anyone's wanted an answer to. And so there's a lot of work going into that too, the improved weather and wind modeling, and then that helps everybody with navigation and power efficiency too. And I think with the amount of work that's going into it, considering how little has been worked in that space before, that could really make a big difference too. We could see that move a long ways.
Fantastic. So, Russ, I want to thank you for taking us above the clouds today. And we've covered the aircraft design, the power systems, the missions, and the challenges. And I think our listeners now have a much deeper understanding of what HAPS and why it matters. And where can people go to learn more about the HAPS Alliance and follow what you're doing?
Yeah, so I mean, we have a website. It's creatively at hapsalliance.org. You can go on there. You can see all the companies that are part of this. You can also see a lot of white papers that we've written about how these systems work, where they're useful, what technologies are involved. And you can get involved. I mean, if this is a space you want to be in, we're always excited to have new members, and we're doing a member get together here in November in New York City. So if you hurry up and sign up now, you can come hang with all of us in person and be with some nerdy high altitude engineers for a few days. I don't see why you'd want to do anything else with your November. So
Excellent. So I will put a link in the show notes and on the screen. And for you, I just ask that you like and subscribe us. We'd love to have you a
very
subscriber. And if
well.
there's any future events where we can come out and film, that would be awesome.
Sure.
And then for our listeners, stay tuned for more conversations at the intersection of technology, energy, and aerospace here in the Watt Hours. So, Russ, thank you so much for doing this interview.
Yeah, it's been great, William. Thanks for having us on, and we love talking about what we do. So no skin off our back. It was great.
Stay safe and make it great. Thank you, sir. Have a great
All
day.
right. Thank you, sir. Yeah.
You're welcome.